Look at this visualization. We are looking at millions of unstructured data packets pouring into a multi-node network architecture. In enterprise big data, this is the reality of ingestion. Logs, sensor readings, and text files flood the system continuously, creating immediate, heavy congestion. This congestion exposes a strict architectural paradox. Hadoop processes this scale of information because it relies on infinite decentralized scalability. But that exact decentralized structure inherently resists centralized enterprise data governance. The nodes are designed to distribute workloads, not to naturally enforce universal rules. Without a governance framework to impose order, this massive storage environment rapidly degrades. What begins as a high-potential data lake becomes a data swamp, an unnavigable, legally non-compliant repository where finding accurate, usable information is nearly impossible. We have partnered with Royal Research for this episode to solve exactly this problem. We're going to utilize their frameworks to architect a secure, legally compliant Hadoop governance model from scratch. Resolving the scale control paradox requires building a specialized, centralized overlay framework. This architecture must sit above the raw data layer and address the specific points of failure inherent in distributed systems. To maintain stability, the governance layer must enforce 4 specific pillars of control: metadata management to provide context, data lineage to ensure traceability, data quality for reliability, and regulatory compliance for legal protection. Effectively governing Hadoop requires an integrated, automated architecture that processes raw data into a legally usable state. Let's build it. This 3D blueprint represents our baseline environment, a bare-bones Hadoop distributed file system, or HDFS. Notice the individual storage nodes. Right now, they operate independently, holding whatever we drop into them. This exposes the inherent vulnerability of a schema-on-read environment. Incoming data packets arrive entirely without context or structure. Until a data scientist actively writes a query to read them, these packets are just unlabeled raw bytes drifting inside the nodes. We fix this by overlaying our first pillar, metadata management. A new operational layer drops over the HDFS blueprint. Now, as data lands, the system automatically attaches contextual tags, metadata, telling us what the data is, where it came from, and who owns it. Through automated tagging upon ingestion, the scattered packets organize. We have established a single source of truth. Every decentralized node now reports to a unified indexing grid, ensuring all users are looking at the exact same definitions. To maintain accuracy across different engineering teams, centralized data dictionaries are deployed. These dictionaries standardize naming conventions, ensuring that a revenue metric from the marketing node matches the revenue metric in the accounting node. Speed is critical here. In distributed architectures, data must be cataloged the millisecond it lands. If a packet enters the environment untagged, it is effectively lost in the noise of a petabyte-scale system. Metadata management is the mandatory prerequisite. Without this foundational cataloging layer, tracking where data goes or enforcing access controls is mathematically impossible. With the data cataloged, we apply Pillar 2, data lineage. This is the process of tracking the continuous journey, movements, and state changes of data across the entire ecosystem. Here is a node graph visualization representing the interface of Apache Atlas, the specific ecosystem tool deployed to automate this tracking. Atlas provides absolute visibility into a packet's lifecycle. We can map a standard transformation sequence. The packet starts as a raw JSON file, gets processed through a MapReduce job, and finally lands as an organized row in a structured Hive table. This tracking mechanism drives a critical operational necessity: impact analysis. If a developer flags an error or proposes a change on the upstream JSON node, Atlas immediately highlights all dependent downstream nodes in red. Impact analysis allows architects to instantly assess the blast radius of a change. Before pushing an update, they know exactly which downstream analytics dashboards will break if that upstream data schema is altered. Working alongside this is data versioning. By taking sequential snapshots of datasets, engineering teams can track exactly how a piece of information evolved over historical timeframes, providing context for long-term analytics. Because transformations and data movements in a Hadoop environment happen thousands of times a minute, relying on manual mapping is a guaranteed point of failure. Automated data lineage provides absolute traceability. Organizations can pull up an executive report and mathematically prove the exact origin of any analytical metric to auditors, regulators, or internal stakeholders. Even with strict lineage tracking, the incoming raw data stream will always contain formatting errors, null values, and anomalies. That is simply the harsh reality of massive-scale ingestion. To prevent corrupted data from reaching end users, we build Pillar 3, Data Quality. This functions as an automated validation checkpoint buried deep within the pipeline. This pipeline schematic illustrates the data routing directly through Apache Hive and Apache Pig. These processing engines act as the primary validation gates. The first automated step is data profiling. The system scans the dataset as it flows, identifying anomalies against predefined rules, highlighting corrupted packets, mismatched dates, or illogical numerical spikes. Next is the cleansing phase. The system automatically corrects minor formatting errors. The corrupted packets that fail the logic rules are split off into a quarantine bin, while the verified, clean data continues down the main pipeline. Machines alone cannot manage this. This introduces collaborative data stewardship. Human stewards are required to oversee the output, investigate the quarantine data, and continually update the automated rule sets as business logic changes. Without rigorous pipeline-level quality validation, the sheer volume of Hadoop data would amplify small input errors across millions of records, rendering enterprise analytics completely untrustworthy. Clean, traceable data is highly valuable, which makes it a target. This brings us to the fourth and most critical pillar, data compliance and security, dictating how sensitive information is legally protected. Look back at our HDFS blueprint. We apply a centralized policy administration layer, Apache Ranger. It blankets the entire Hadoop architecture, intercepting every single query before it reaches the disk. Ranger serves as the central evaluation point for authorization. When these users request data, Ranger validates their identity against the global policy store and applies specific permission sets tailored to their department. Role-based access control ensures users only receive the permissions strictly necessary for their specific tasks. This principle of least privilege prevents the overexposure of data across the decentralized nodes. This is an absolute necessity to meet the strict legal requirements of regulations like GDPR and HIPAA, which mandate severe financial penalties for exposing personally identifiable information, or PII. To maintain compliance, Ranger uses real-time data masking and anonymization. Watch this table. As an unauthorized user's query requests this dataset, the column containing names and social security numbers is dynamically scrambled into asterisks. The masking protects the PII before it ever reaches the end user. Crucially, the aggregate numerical data in the adjacent columns remains unmasked, maintaining the security of the individual without breaking the mathematical utility of the overall dataset. Furthermore, comprehensive auditing capabilities log every single data access request, modification, and movement. If an auditor asks who viewed a specific patient record last Tuesday at 4 p.m., the log provides an indisputable answer. Through Ranger, legal compliance requirements are hard-coded directly into the data access path, making policy adherence an inherent property of the system architecture. We now see the complete architecture operating over the Hadoop cluster. HDFS forms the base, governed by metadata, mapped by Atlas, validated by Hive and Pig, secured by Ranger. Watch a dataset's lifecycle, tagged, mapped, cleansed, and dynamically masked before reaching a secure dashboard. Operating this stack requires solving a critical challenge, interoperability. Ensuring diverse ecosystem tools like Atlas, Ranger, and Pig communicate with each other without creating friction or latency in the pipeline. Achieving this seamless integration typically requires centralized governance platforms, utilizing environments like the Cloudera Data Platform or Hortonworks Dataflow to bind the tools into a single control plane. Reliable governance depends on integrating these automated layers into the data lifecycle, starting from the moment of initial ingestion. Infinite scalability and absolute control are not mutually exclusive. When the right metadata, lineage, quality, and compliance frameworks are applied, the scale control paradox is solved. We'd like to thank our partner, Royal Research, for providing the underlying frameworks discussed in this episode. To explore comprehensive enterprise solutions for your own architecture, visit the Royal Research link in the description below.